Welcome. In this video, we'll be learning how to use the HFSS Antenna Toolkit to create simple antennas rapidly. We'll be creating a 5.8 GHz microstrip patch antenna with custom parameters, simulating the antenna, and then viewing and exporting the data for post-processing. Before we start this video, I'll assume you know a little bit about HFSS, such as creating projects and navigating the software. So without any further ado, let's get started. So once you've gone ahead and opened the HFSS application and Ansys Electronics desktop, go ahead and enable ACT extensions from the View drop-down menu. This will open a panel on the right side. Go ahead and click Launch Wizards and select the HFSS Antenna Toolkit. This toolkit is pretty powerful. It'll allow you to create various types of antennas with little effort. In most cases, you can simply input a center frequency, hit synthesis, and it'll generate the dimensions for you that it assumes are ideal for an antenna at that frequency. For us, we're going to stick with a patch antenna and then a rectangular inset-fed patch antenna to be specific. The center frequency for this will be 5.8 GHz, and if we just hit synthesis, it'll auto-generate many different dimensions and populate them here for us. And we could at this point go ahead and finish and create the model. But we have a set of dimensions that were designed from textbook equations, and we have an antenna model that we'll build in a separate video that this antenna right here from the toolkit will be one-to-one match with. We're going to simulate both and compare that to a real-life prototype data set and compare all the results in a later video to see the difference between each build of this antenna. So the patch X dimension and Y dimension, you only need to change the Y dimension here. 2.04 is the same for our model. We have 1.6725 for the Y dimension, and be careful to put in all the right digits. If you happen to put in the wrong digit to one of these dimensions, it could cause simulation issues later on down the road. We can keep the material as Duroid, and the substrate height is alright at 0.1575 centimeters or 1.575 millimeters. But this board is going to be a 10 centimeter square substrate. So we're going to change both the substrate dimension X and Y to 10 centimeters. For the feed dimensions, the inset distance, we're going to go ahead and alter to 0.6. Then this inset gap is going to be really small. It's going to be 0.0275. So almost a factor of 10 smaller than what the HFSS Antenna Toolkit would have created for us. The feed width will be 0.485. And then the feed length, quite long to get to the edge of the board. That'll be 4.16375. So 4.16375. All right, let me just look over all these dimensions. They look good. Once you're ready to go, hit finish. And the Antenna Toolkit will create for you a project. It'll create for you a model. And in fact, it'll even create for you all of the reports necessary to view different qualities that your antenna has. So if we expand this window, we can see our model has already been made. We can now close the ACT extensions window. So at this point, I'll explain some of the features that the HFSS Antenna Toolkit has populated into the project here on the left side, and then we'll prepare the antenna for simulation later on. First, I'll go over these boundaries. If you drop down and open up this menu, you can see that there's the antenna metal and then the ground metal below it. This is, of course, the antenna and then the ground plane, respectively. What this does is defines the two as electrical conductors so the simulation program can recognize them appropriately. Below that, we have this thing called Open1, which if we look at it is clearly just a box. All this does is aids the program in simulating the 3D emitted fields around the antenna. Next, I'll go into the excitations. So we have a port, and that's right here, this rectangle that's at the edge of the board. And if we click on excitations 1, then we can see that this thing is highlighted. And so what it means is that the voltage wave that is the simulation's agent to calculate the emitted waves will be inputted right here at the port and thus connect the antenna and ground together using the ground plane as a reference. Below that is the analysis, and if we drop down and open up these two menus, we can go ahead and see that there's two already populated. So the far field sweep, if we double click that, we can open it up and see what it is. It's a discrete type of sweep, so it calculates each frequency individually, and it's a linear count from about 3 to 8.7 gigahertz. There's only 3 points. Around each frequency, far fields don't seem to change very much, and so 3 frequency points is enough to kind of characterize the far field pattern of this antenna across a very large bandwidth of operation. The most important thing to remember here is that the Save Fields button is selected, and that'll allow us to actually see the 3D fields and 2D fields on a polar plot later on when we complete the simulation. If it wasn't clicked, it wouldn't save these fields, and that will be useful for the next solution type, which we'll go into now. So the S-parameter sweep, short S-param sweep, will just allow us to see the scattering parameters of the antenna. It won't show us any far field data, and we know that because it won't save the fields as this button is not selected. And also, it's using an interpolating sweep type. This calculates 100 points, but doesn't do them all individually. It does a select group of them and then interpolates data in between to yield an approximate solution across the same frequency span. This one will simulate a lot faster, but will only get us results with regard to scattering parameters. Below that, we have the results. We have different reports that are pre-populated and that when a simulation is complete will have information in them, which we can then view and process and export for comparison. We'll be putting in a few reports of our own later on. So at this point, we'll go ahead and ready the antenna for simulation. We'll go ahead and do a validation check and then make sure all of our analyses are proper. And then we'll go ahead and simulate both and then look at the data afterward. So the first thing to do, but right before you simulate, is run a validation check. That can be done by going to simulation and hitting validate. And if we click it for this model, we see an error under the boundaries and excitations menu. I've gone ahead and explored this, and it's merely a rounding error caused by the creation through the HFSS antenna toolkit. If we hit HFSS and go down to design properties, we will see all the dimensions that we inputted, and if we look down at the feed length, we remember that it was 0.16375. The program seemed to have rounded it, and if we were to reapply this, the model would be fixed. Now all we need to do is just redo the excitation, and if we simply delete the old one, we can go ahead and replace it with our own, which will understand that the antenna and ground plane are the two conductors to reference from. So highlight the port, click on it, then right click, assign excitation. Under port, go ahead and put a terminal lumped port, and then select ground as the reference, since of course this is the ground itself. Click OK, and then we fixed it. Now if we run a validation check, we have green check marks, which means we are good to simulate. So at this point, I'll run both the far field sweep and then the S-param sweep together. It might take a few minutes, and so I'll simulate this and resume the video once they're both done. To go ahead and simulate, you can right-click Analysis and hit Analyze All. It will run through every solution you've defined and simulate that. So I'll go ahead and do that and be back when it's finished. So now that the simulation is finished, we'll go ahead and explore some of the data. We know the simulation has finished because there's a message in the Message Manager tab, and we can see if we look at this that a discrete frequency sweep has been complete and an interpolating frequency sweep with 100 points was completed on the server. And so that means our simulation completed with no errors. So we can go ahead and close these two tabs and move on to looking at the data. We can see on the left side under the results drop-down menu, a few reports have already been added by the HFSS antenna toolkit. I've gone ahead and opened some of these just to look at them. That's why the color is present here in the little picture to the left. The return loss and input impedance do have data associated with them. I just haven't opened these plots yet. So if we go ahead and click on one of them, it'll open the plot itself. Here we can see a 3D polar plot of the total gain at one frequency. If we wanted to see more details, we could open the drop down menu and double click on this little line here, and that applies for most of these plots as well. And we'll go ahead and do that. So this window tells you essentially all you need to know about plots, and you can customize what is plotted, how it's presented, and what frequencies you're selecting from. So on the left side, we have the context that gives context to what is being plotted. You can see under solution, we've selected last adaptive, but we really want to select the FF sweep or the far field sweep simulation that was just completed. This will allow us to take frequency points from that sweep simulation rather than just the one last adaptive frequency, which HFSS uses simply to build the model that will simulate at later. The geometries are essentially combinations and definitions of angles to plot and record data in, and we can leave it the way it is for now. Under the trace itself, there's a variety of settings. There are the primary and secondary sweeps, so it tells you that phi and theta at all angles and combinations will be plotted, and that's indeed what we see down here. And then under the magnitude, we can see the equation for what's being plotted, which we don't have to manually write. We can use these menus here. So under gain, we have gain total, which is what we want to plot. Then the function, of course, is dB. And if we were to apply this, nothing would change, of course. Under families, we're able to select which frequency we want to plot. So currently it's at 5.8 gigahertz, the center frequency of the antenna. If we clicked edit, you could see about 3 and 8.7 gigahertz are there as well. But if you were to select the last adaptive, you'd only have that one frequency in the center to select from. So it's essential that you change the solution under the context there. So let's go ahead and change the frequency and watch the plot change itself. And now we can see a much different representation. So of course, we're mostly seeing 2D plots, 2D polar plots of the gain, and so that's what this next report is. If we open that, we can see a different format. It's in this 2D polar, and it's got two different plots on it at once. You can see on the legend that the red one is at phi equals 0 degrees, and the green one is at phi equals 90. Relatively similar, and something we'd expect by seeing the 3D model from the previous plot, that these two principal plane cuts are not perfect replicas of each other. Beneath that, we have 2D gain total stacked. So we have stacked plots essentially, where we have in 2 dimensions the gain at different frequencies and combinations of phi. So we have, for instance, 5.8 gigahertz at 0 degrees, and then the same frequency at 90 degrees, all plotted for all frequencies right next to each other, on top of each other. And so this is good to compare multiple plots. Below that, we have the return loss and impedance, but before I go on to that, I'll talk about how to export all this data. Exporting 2D plots, such as the polar plot, is relatively simple. You click on it, right-click, export, and then we have the ability to save the file. I usually save it in a CSV, but there are a variety of different data formats. You can save the image directly or the data as numerical values. And then if there's more than one curve, you'll want to select use separate columns for curves, especially if you're saving it as a CSV. It makes post-processing the data a lot easier. And then the same thing applies for the stacked gain plots. You can export those as a CSV, or if you wanted to, perhaps as a PNG, so just to save the image, and then different settings apply here. The image size can be changed. You can change the different resolutions and whatnot. But for a CSV, you'll definitely want to select separate columns for curves if there are more than one curves present. So we'll go ahead and open the return loss, and there's nothing here. So perhaps this wasn't the right type of plot for HFSS to use, which is okay. We can create our own. Under results, you can click on it and create different reports here, but this isn't as informative as clicking on the results tab up top and then going to terminal or modal or far fields report and then plotting what we want. Terminal solution data report gives us these S parameters that we've been simulating for, and we want a 2D plot just like this. And then we can go ahead and plot from the S parameter sweep the reflection coefficient of our antenna. So we want to select this S param sweep because remember, the primary sweep is frequency, and we want all the frequencies across our simulation bandwidth to be plotted. And of course, the domain is sweep. So to find the reflection coefficient of the antenna, we need to go to the terminal S parameter. There's also Y and Z and a few others. But under the S parameter, there's only one port, so you only have one quantity here. And then of course you want to plot that in dB. If we click new report, we get this, and we can see that there's a local minimum, and we don't know which frequency it is because there's not enough ticks. So we can right click on the line itself, make sure we selected it, and then click marker. We can either add a general marker, which we can drag, or a minimum. In this case, I want to add a minimum, and M1 marker 1 has been placed. On the top left, you see the marker legend. At 5.83 gigahertz, the reflection coefficient is at minus 18.8 dB. So verifying our design. And then we can of course add a regular marker and then place it anywhere we want along the line. Let's just say here at 5.9465 gigahertz, we have minus 7.7. And we can export this as well. We won't have to do any fancy setting changes because it's only one curve. And now we can see the reflection coefficient of our antenna. The input impedance as well has not plotted properly, but that's all right. We don't usually want to view it in a Smith chart, but if we did, we could go to Terminal Solution Data Report, open the Smith chart option, and then replot the data here as well. Not in dB, just as it is, and make sure under families there's nothing to change. Since there are no angles to choose from, there won't be anything here to change. So if we generate new report, we see only 3 frequency points. That's because we forgot to change the context. We're still in our far field sweep. So if you see a data report that doesn't make sense, it's probably because you forgot to select the right solution. So now if we apply that, we can see a more realistic plot that we understand and matches the data more properly. So if we go ahead and add a marker to this, we can see at which frequency we're looking at, and this seems to be at 5.88, so that was a good guess. But if I drag it to the left, perhaps it would be closer to 5.8, and indeed we have the angle of magnitude there, showing us that the reflection coefficient of our antenna is very close to the center of the Smith chart at the design frequency of 5.8. Now, my cursor is currently in marker mode, so if I keep clicking, it'll add markers. That's why we have M1 and M2, which are the exact same because I double-clicked on the same point twice. You can go ahead and right-click, end marker mode, and then you can click on the line without fear of adding unnecessary markers. So that's all the results that we have. There are a variety of different ones that you can pick from. There's different ways to plot it. Under the results ribbon here, you can find different terminal solution reports, different ways to plot the same data. You can stack it all together. If you wanted to plot the input impedance with a 2D plot to show the real and imaginary parts separately, you could do that. All you would have to do is go to the S parameter sweep solution right here, find the terminal Z parameter category, and then plot that only option in imaginary and real formats. And then you'd have your input impedance plotted across frequency like that. I recommend you go through the various types of reports to see what HFSS has to offer and what you can do with the data that's been generated by the simulation. I'll go ahead and export the data that we have now, some of it so that we can compare it later on to the data from the model that we'll make from scratch, another patch antenna which is 1:1 in dimensions to this one, and then a fabricated prototype that's been tested in the lab. So I hope to see you in those next videos.